All right. So the hint was to expand the whole thing completely first. So expanding involves three things. Powers bring down in front, multiplication we turn to addition, and division we change to subtraction. So let me get my pen here. All right, so I'm going to start by saying log base 2 of 81. That is multiplied by the x to the fourth. So if I want to expand that, I change it to what operation? Addition. So log base 2 of x to the fourth. And then that's divided by y to the third, so I change that to what operation? Minus log y to the third. Okay, now the 4 I can write down in front of the log base 2 of x. And the 3 I can bring down in front of the log base 2 of y. Good there? Okay, and I'll get to that 81. I'll come back to that in a minute. Log base 2 of x and log base 2 of y. Now, if you look up there, you know those pieces of information. Log base 2 of x is 2.6. Log base 2 of y, you look at the given information, is 4. So that's all set. Those are things that we can calculate in a minute. The only issue we're going to run into here is the 81. The only piece of information I'm given about a log of a number is log base 2 of 3. So you have to figure out how can you write 81 in terms of 3. It is 3 to the fourth power. And if I write it like that, what can I do with that power? Bring it down in front. So I have 4 times log base 2 of 3. I know what log base 2 of 3 is. It's 1.58. Plus the 4 times 2.6 minus the 3 times 4. Okay, and then I just put all that in my calculator. So I have 4.72. There's going to be a basic calculator and graphic calculator. Yes. Yeah. I don't remember what part it is on. It is on the graphic calculator part. As a take-home quiz. Yes, any questions here? Okay. All right, so we are going to do the last section today then, 4.4, which is exponential and logarithmic equations, which becomes a little bit of already with like our first formulation, so we're going to handle that a little bit. All right. Ready? Okay. All right. So let's start with some exponential equations. Okay. This first group of problems we're going to talk about are exponential equations where you are able to obtain the same base on both sides. Okay. When we say obtain the same base, we mean make it look like 2 to a power equals 2 to a power, or 5 to a power equals 5 to a power, where you have the base of the same number on each side of your equation. So, for example, in this first one, 3 to the x equals 243. If I want to solve by obtaining the same base, I write 243 as a power of 3, which you could do a little guess and check to figure that out. 3 to what power would give me 243? 5. So if I can write it like this, 3 to the x power equals 3 to the fifth, the only way this equation is true is if my powers are equal to each other. So at this point, you can just drop the base of 3 and compare your powers. And actually here you're done. You don't have anything else to solve for. Your answer is x equals 5, which you could very easily then plug that back into the equation and make sure it works. Okay, so let's try the next one. 8 to the x equals 4. 8 and 4 can both be written as powers of what number? 2. 8 is 2 to what power? 2 to the third, and then there's still that x there. And 4 is 2 to what power? 2 squared. What do I do with that 3 and the x if they're separated with a parentheses? That's one of our exponent rules. Multiply. So I have 2 to the 3x equals 2 to the second. So 2 to the 3x equals 2 to the second. The only way for that to be true is if 3x equals 2. And then my answer is x equals what? 2/3. Okay. 4, go ahead. 8 to the 1/2. Square root 8 is not such a square.
Oh, square root.
Yeah, that's what you get. 1/2 is going to get it. All right, so 4 to the absolute value x equals 128. 4 and 128 can be written as powers of what? Always guess and check your way through it if you need to a little bit there. Is 128 a power of 4? I'm not sure. No. So what about 2? The 2 work? And my only other option for 4. 2 squared, and then 2 to the 7th. Okay, and again, the 2 and the absolute value x are just multiplied together there. So I have 2 to the 2 absolute value x equals 2 to the 7th. So I can say 2 absolute value x must equal 7. How do we solve for x? Divide by 2, so the absolute value of x must equal, you could say 3.5 or 7/2. So there are 2 answers to this equation. What are they? Plus and minus 3.5 or plus and minus 7/2. Both of those numbers, if I put them inside the absolute value, would become a positive 7/2. Okay? Any questions? All right, let's try some tougher ones. 9 to the x equals 3 to the x plus 1. 9 and 3 can both be written as powers of 3. So I have 3 squared, and then again there's that x there, those will just be multiplied together, and 3 to the x plus 1. So this time we're showing what happens if I have addition and subtraction of my powers. Same piece to start, we want to obtain the common base on each side, drop the bases, and I have 2x equals x plus 1. Solve for x now. What do you do first? Subtract x, which will just give me a 1x equals 1, and then x equals 1. Okay. What am I going to do on the next one? 3/5 to the x equals 125 over 27. Okay, so what could I rewrite here? 3 and 5, you don't really have any choices, right? They're prime numbers. I'm not going to be able to write them as power of anything. So let's start with the right side. 125, what could I do with that? That's 5 to the 3rd, power of 5. Okay. What's 27? 3 to the 3rd. So this one, you may be able to actually look at it and figure out what number is missing there. What number does x need to be to make that equation true? It needs to be negative because we want our fraction to flip. What else? I heard somebody say it. -3. Yeah. So we want a power of 3, which would give me 3 to the 3rd and 5 to the 3rd. And then because my numerator and denominator flips, we want it to be negative. You could probably get fancier by putting all that together and factoring out 3 and things like that. But most of the time, it's just going to be able to, once you've obtained that common base, you can probably see what your answer is going to be. Okay, the last one's the trickiest one. 3 to the x equals 9 to the x plus 1 times 27 to the 1 minus 3x. So here I have 3 bases. 3, 9, and 27 are all powers of what? 3. Okay, so I have 3 to the x. 9 is 3 to what power? Second, and remember that's multiplied by the x minus 1. You need a parentheses there, so you are going to have to distribute. And 27 is 3 to what power? 3. And I have 1 minus 3x. Now, you are not ready to drop the bases yet, and here's why. I need it to look like 3 to a power equals 3 to a power. So I need to be able to put those two on the right together. How can I put them together? Think about your exponent rules. Those 3's are multiplied with the same base. Exponent rules say, what do I do with the powers? Add them together. So it's going to be 3, base stays the same, and I'm going to add those two exponents. So 2x minus 1 plus 3, 1 minus 3x. What would you do if they were divided to combine them together? You would subtract the exponents. Now this is our goal. 3 to the power equals 3 to the power. I can drop the bases and say, well, if that's true, then x must equal all this other stuff. How do I solve for x? Distribute my couple of mixtures. I'm going to have 2x minus 2 plus 3 minus 9x. Second like term, so 2x negative 9x, that's negative 7x. Negative 2 and 3, positive 1. Maybe move my 7x to the other side. So I have 1x and 7x, which will give me 8x equals 1. So x is 1/8. Okay. So if you do see you have multiple bases on one side, just use your exponent rules to put them together. Add, subtract, whatever. All right, any questions obtaining the same base? Okay, so that's probably more the special case than the rule, I would say. In general, you're going to have problems that look something like this. Like here I have a 2 and a 17 and a 5. Those are not something that I can obtain the same base. I can't write them all as the same power of a number. So we're going to use logs to help us solve instead. And these are going to be our steps to solve using logs. By the way, this method would also work for those common base problems that we just did. So if you got stuck on those and you weren't sure like how to write them as the same base and what to drop, you could use logs, what we're about to do for those if you want. Okay, so first step is we want to isolate the exponential expression. So the base to the power, we want to get it alone. We don't want anything multiplied, added, subtracted, divided by it. Then you're going to take either the common or the natural log of both sides. Technically, you can use any log base, but common and natural log are going to be buttons in red calculator and basic calculators, so we want to stick with those. Then you're going to use the power rule, which says you can take your exponent and bring it down in front. That's where our variable will be, and then we'll be able to solve for our variable. Okay, so 4-step process. Isolate the exponential equation, take the log or the natural log of both sides, the power rule to bring the exponent down, and then solve for the variable. So we did one problem like this yesterday when we were talking about the change of base property. I think it was like 7 to the x equals 6. We used these steps. We took the log of both sides, we brought the x down, and then we divided the log number to get the x alone. So we'll just be kind of doing some more complicated vision. Figure out what they need? Okay. Okay. All right, so let's try these. 5 times 2 to the x minus 3 equals 17. The first step, isolate the power. Okay, so in this case, my base is 2 to the x minus 3. I want to get that alone. So what do I do first? Divide both sides by 5. So I have 2 to the x minus 3 equals, I'm just going to leave it as 17. Okay, so my base to the power is alone. I'm going to take the log of both sides. I'm just going to use a common log, but remember you could also use a natural log here. Okay, so why do we want a log there? If I put a log in this problem, I can use my log property that says that power x minus 3 can come down in front of the term. So x minus 3, I'm going to keep those guys together, put them in parentheses. Log 2 equals log 17. Okay. Now, log of 2 and log of 17/5 are just numbers. You can type them in the calculator to figure out what they are approximately equal to. So you can manipulate them as much as you want. This is really just a linear equation in disguise. There's nothing fancy about this. So option 1 is you can distribute the log through. I would just get rid of it. Multiply by the parentheses. I would just divide both sides by log 2. So then you have x minus 3 equals, and now that is what you're going to put in your calculator. Log of 17/5 over log of 2. And let's round to 3 decimal places. Obviously, the less you round, the better. Divided by a log of 2. We get 1.76. 6, round to 3. And then last step, add 3. So it's going to be 4.766. So it's an equation. You can take your answer, plug it back in, make sure it works. Okay. All right, so let's try the next one. We have 5 to the 2x minus 3 equals 3 to the x plus 1. Okay, so first step is isolate the base to the power. Well, we have two bases here, but both of them are actually isolated already. In each of those sides there, we don't have anything multiplied, divided, added, subtracted by base, so we're good. Second step is we're going to take the log of both sides. First one that we apply here. The log of this equals log of this. And now because I have a log there, what can I do next? Bring the next one is down. So 2x minus 3 comes down in front of this log. And x plus 1 comes down in front of this log. Again, you can distribute this one if you want. I would just divide by one of them. It doesn't matter. I'm going to divide by log 5 just to get that one to the other side, but you can always divide by log 3 as well. Those are going to cancel here. 2x minus 3 equals x plus 1 I'll just bring down, and I'm going to simplify that log 3 over log 5. And that's what you're typing in your calculator, log 3 over log 5. So this is where we're going to have to round a little bit. So that gives me to 3 decimal places, 0.683. We take that up. Okay, so I'm going to distribute that through. So I'm going to place the point. So I have 2x minus 3 equals 0.683x plus 0.683. I get my x terms together on the same side, so I'm going to subtract 0.683x. So that's going to give me 1.317x. And actually, while we're at it, we just add the 3 to the other side too. So 3.683. Just getting like terms on either side of the equation there. And last step, divide. So 3.683 divided by 1.317. 2.7965. I'm going to say 2.800. We're going to round it to 3 decimal places there. Okay, which again, I got 2.7965. So the 6 rounds up to the 7. I don't know why I did that. That doesn't make sense at all. Don't say I'm rounding for some reason. Thank you for catching that. That's bad. Don't do that. So 797. Yeah. I don't know what I was thinking. I was thinking 2 decimal places. Okay. Any questions? All right. Yes, because you didn't round correctly. So I would have marked my own answer on there. 1.0. All right, so last exponential problem. 2 times 3 to the x minus 1 equals 5 to the x plus 1. Okay, so again, we have two bases here. One of them is isolated, the 5 to the x plus 1, that one's good, but the 3 is not. And here's the issue you're going to run into here. Even if I try to get rid of that 2, I'm going to move to the other side, and then that one's not going to be isolated. So you're going to go back and forth. There's no way you can get both of these powers with nothing in front of them. So you're stuck at this point. You have to start by taking the log, and I'll show you what to do if you get stuck. Okay? Take the log of both sides first. On the right, x plus 1 is on the 5, so I can bring it down. Now here's the problem on the left. I can't bring the x minus 1 down because it's not a power on the 2. It's only a power on the 3. So I need to separate the 2 from the 3. How can I do that? Change it to addition. Use your log properties. Make it log 2 plus log 3 to the x minus 1. Now you can bring that power down. So log 2 plus x minus 1 log 3 equals x plus 1 log 5. Now it looks nasty, but remember log 2, log 3, log 5, those are all just something you can get a decimal approximation for in your calculator. So it really is just a linear equation. My next step, I would divide by one of the logs. Let's go ahead and divide by log 5. because that's the only guy on that side. Now I'm going to divide because it's addition here. Every term by log 5. So the x minus 1 is most under the log 3. Okay. So two things you're going to type in your calculator. Log 2 divided by log 5, which gives me 3 decimal places, 0.431. And then log 3 divided by log 5, which is what we did before, that was 0.683. And that's multiplied by the x minus 1. Okay, so again, just a linear equation now. Let's start distributing, combining like terms, all those wonderful things. 0.431 plus I distribute my 683 through, I get 683x minus 0.683 equals x plus 1. Like terms together on that side, I have 0.431 and negative 0.683. This is going to give me negative 0.252 plus 0.683x equals x plus 1. Let's say I want to subtract my 0.683x to the other side. That's how you want to do these things out of here. Last here, and I will subtract 1 on both sides. So on the left, I'm going to have negative 1.252. My x's are going to cancel. On the right, I'm going to have, let's see, a 1x minus 0.683, so 0.317x. And then again, my 1's cancel. Divide by 0.317. I'm going to get x equals, let's see, so 3 decimal places, negative 3.9495, so I think it's 950. I did that one right. 3 decimal places. Okay. It's about as complicated as those are going to get. Again, it's not too bad. You just have to be careful when you bring those powers down that you separate any terms first if the power doesn't apply to it. Good? All right. So next problem is an interest rate problem. We'll need one of our formulas. What interest rate is required to triple your investment of P dollars in 5 years if the interest is compounded quarterly? What formula would we be using if it's compounded quarterly? Not her. The one left. This one. Okay. Do you know what A is going to be? 3P. Or triple R rate investment. We know R. No, that's what we're solving for. N. 4. And then 4 again. Number of years. 5. Okay, what would you do first to solve for R? Cancel what? Okay, so we're dividing by P on both sides, which means that P is going to cancel. Yep, 3. So 3 equals 1 plus R over 4, and I'm just going to do that 4 times 5. It is 20th power. I do not need logs to solve this problem. So remember, you only need logs if your variable is in the exponent. Is my variable in the exponent? No. So I can get rid of that power now. If it was a squared, what would we do? Square root. If it was a cubed, what would we do? Cube root. It's a 20th power. So what are we going to do to get rid of it? 20th root, which is the same as the 1/20th power on both sides. If you know the exponent, you can just use the reciprocal. So those are going to cancel out. 1 plus R over 4 equals whatever the 1/20th power is, 20th root of 3. So I get 1 point, and look at those 2 decimal places here. In your calculator, though, really, you guys could just keep using the previous answer for this one. Next thing you would do is subtract 1. So R over 4. And the next thing you would do is multiply by 4. But again, you can do that all in the calculator. Minus 1 from the previous answer times 4 from the previous answer. So I get R equals 0.2259. So I round it to 4 decimal places, which is what interest rate? 22.59%. Okay, so I wanted to show you that one because we don't always have to use a log if it's an exponential equation. If we know what the variable is, or know what the exponent is, if our variable is somewhere else, you can just use reciprocal powers. Okay? All right, so the last couple problems we're going to do are what happens if you have a logarithmic equation. So logarithmic means the original equation contains a log, like the two you see down here. And there are 2 different things that could happen depending on what the problem looks like. The first is if you have a single log in a problem like the ones you see at the bottom here. If you have a single log, we isolate it, and then we're going to write the expression with exponents instead. Or with exponents, we'll be able to solve. Second, let's say you have more than one log in the problem. If you have more than one log, you're going to condense using our properties from the last section. And then you can either write with exponents or you'll be able to drop your log and you'll see we'll do one of each, what that looks like. Okay? But in either way, you want to be able to either condense the logs or get the logs by themselves to start. So let's go ahead and do these 2 at the bottom. These are going to be quick ones. If I have 4 plus 3 log base 2 of x equals 1, and I want to solve it, I want to get that log base 2 of x alone first. Oh, there we go. So how do I get log base 2 of x alone? What would be your first step? Minus 4. Divide by 3, so log base 2 of x equals -1. So now that log is alone. There's nothing added, subtract, multiply, or divided by it. So at this point, you write the expression with powers instead of with logs. So what does it look like with powers? 2 to the negative first equals x. And actually, we're basically solved for x, then 2 to the negative first is what? 1/2. That's our answer. Okay, which then again you can plug back in and check. Let's try the one with the natural log. I have 1 plus 2, natural log x equals 4. How do you isolate the natural log? Subtract 1. So 3. Divide by 2. Leave it as 3/2. And now writing this with exponents. If it's a natural log, what base is that? E to the 3/2 power equals x. Now x is alone. If MathXL wants an exact answer, this is it. E to the 3/2 power, because E is an irrational number. At this point, anything you type in is going to be rounded. Make sure you're careful with what it's asking for. So e to the 1.5 power gives me about, that's done my places here, 4.48. Okay. Yes. Base 10. Yeah, but there wasn't a subnotation, it's a common log base 10. The only thing you have to be careful with logarithmic equations is, remember, part of our definition of logs said if we have log base a of x, which is part of our domain, that the x must be greater than 0. So what could happen in these problems is you get an answer that is extraneous, meaning if you plug it back in to wherever your log is, if you get a negative number there that's outside of the domain, it would be an extraneous solution and you would throw it out. Now both of these were okay. If I plug a 1/2 in, my log value is positive. If I plug 4.48 in, my log value is positive. It's good. But you always want to check those at the end because it's possible an answer won't check. And you'll know that because when you try to type it back in, it's going to tell you domain error or something like that in your calculator. Okay, these are our last 2 problems. Multiple logs in one problem. Log base 4 of x plus log base 4 of x plus 1 equals log base 4 of x minus 1 plus log base 4 of 6. So this is an example where you have multiple logs, all of the same base. So first idea here is we want to condense it in as few logs as possible in the problem. On both sides, my logs are added together. So if I want to condense, that addition will change to what? Multiplication. Okay, so log base 4, the base stays the same, and I'm just going to multiply what's inside. X times x plus 1. You can do either. Yep, same thing on the other side. Log base 4 is 6 times x minus 1. So here's the first example what can happen. If you have multiple logs of the same base on each side, you can compare them kind of like what we did with the exponents of the same base. Before, if I had 4 to a power equals 4 to a power, I could drop the 4s and compare the powers. If you have logs of the same base on both sides, you can say if log base 4 of that is equal to log base 4 of that, I can drop the logs and say, well, that's only true if what I'm taking the log of, this guy and this guy are equal to one another. And again, I can do that because I have that same log base on each side. I can do with the bases of the powers. So now we can distribute x squared plus x, 6x minus 6. This is a quadratic now. So next thing I'm going to do is shift it all over to one side, get it equal to 0. X squared will be a minus 5x, not plus 6. How does that factor? Negative 3 and negative 2. Okay, so x equals what? 3. So now you want to go back to your problem and look at, would 3 or 2 make any of my logs in the original problem negative? We're going to look at that minus 1. If I plug either of those in, would I have a negative inside the log? No, so we're good. Both these solutions work. Okay? Last problem. Log base 3 of x minus 8 plus log base 3 of x equals 2. So again, I have multiple logs. First step is going to be to condense them. It's addition between the logs, so I change the addition to what? Multiplication again. Log base 3, I want to multiply x times x minus 8 equals 2. In the last problem, I had a log of the same base on each side, so I could just drop it. In this problem, I don't. I don't have a log base 3 there, so I can't just drop it. But I've created one log that's isolated. So if I have one log that's isolated, what can I do next? Write it as an exponent. So it's kind of a combination of the two now. We condensed, and now because we have one log, we can write with exponents. What does it look like with exponents? X times x minus 8. Okay, 3 squared gives me 9. X squared minus 8x. Again, I have a quadratic. So they're equal to 0. Does it factor? Negative 9. Positive 1. So what does x equal? Negative 1 and negative 1 and 9. Okay, so now look back. Do both of those make my logs positive? No, we have an issue. Where's my issue? Negative 1, if you plug it back in actually either place, is going to make what's inside both of those logs a negative number. Remember, you can only take the log of a positive number. So we say that that solution is extraneous. So you can just cross it off and say 9 is the only solution. It is possible that both solutions could be extraneous. So you would just cross them off and say the problem has no solution if that happens. Was that your question? Okay. So just make sure you check with those. And again, that's only going to happen with the log problems because those have domain restrictions. The exponential equations, you don't have to worry about that.